This meeting is being recorded.
I'm going to be giving part of the presentation, and then Marcos Campos will provide the last part of the presentation. One important notice is that we are recording this webinar, and we're going to share it. So if any of you have problems with this, I think now is the time to take measures. So overview. We're going to just briefly let you know what the NERO network it is. It's going to be 3-4 slides just explaining you the basic. Second, we will show you how to reconstruct wildfire spread using satellite data. And then third, we're going to show you the NERO fire collection app, fire spread collection application. So what's the NERO network? The NERO network is a cost action funded by the European Union. It basically funds activities around a certain topic and network activities. So it's not funding neither equipment, neither human resources. And the NERO network topic is extreme wildfires. And the challenge is to coordinate international research on extreme wildfires across Europe and outside of Europe, of course, if possible. To make research outcomes applicable to the operations field, engage researchers and practitioners, and co-creating knowledge, foster capacity building, which is basically what we're doing here, and of course, increase overall awareness about this specific topic. You can know more in the website. Just briefly telling you that the NERO network is divided in 4 work packages, or 4 work groups, sorry. The first one is historical extreme wildfires, which is extremely correlated with what we're going to discuss and be talking in the next 2 hours. So basically reconstructing past extreme wildfires and understanding its behavior, and then laying the foundations for the next work group, which is process-based analysis of extreme fire behavior, meaning that after we reconstructed the observed fire spread and fire behavior, we're going to try to understand it and generate knowledge that can be used both by researchers and, of course, by practitioners also. The work group 3 is the capacity building, which is part of this webinar. Is the NERO Cafe webinar is one of the activities of this work group of capacity building. So it's basically giving you knowledge and tools, either directly from what is generated inside the NERO network or outside of the NERO network. So giving researchers and practitioners the tools and knowledge to cope with wildfires and explicitly wildfire behavior, extreme wildfire behavior. And then as a broader work group, communication and outreach, which basically wants to disseminate all of the work that is done in the NERO network. So this is a really brief presentation of the NERO network. So besides the work that we are doing in the 4 work groups that I mentioned before, one of the, I think, most interesting things that NERO can offer is the networking. So we have short-term scientific missions, which are aimed to support the mobility of either practitioners or researchers across countries, working on topics that are, of course, related with NERO. We have virtual mobility grants, ITC conference funding, and dissemination conference funding. So please visit the webpage if you want more detailed information. There are a lot of opportunities. There's money to be spent, which is important. And so it's just a matter of grabbing the opportunity. So that's my very brief description of NERO. We are currently, we have participants from around 30 countries, over 150 participants. If you want to join the NERO network, just go to the website and join us. So, second topic, reconstruction of wildfire spread using satellite data. So, Let me just give you a brief outline of what we're going to talk. I'll try to give you a very light introduction or a very basic introduction to the fundamentals of remote sensing. We'll then describe some of the satellites and products that are most relevant. They're freely available, easy to use, and most relevant for the fire topic or the fire spread topic. And then we're going to work on a practical example. We will not be able to do, let's say, kind of an exercise altogether. It's not practical in an online workshop of 2 hours. But I think all of the tools and all of the processes needed to reconstruct the example that I am going to show you are in the presentation. Regarding expectations, so an objective and then expectations. So the objective is to provide both researchers and practitioners the basic knowledge on remote sensing and satellites. That's very important. And then practical and easy to use tools to reconstruct the spread of a wildfire in any part of the world. Now, this is extremely connected with WG1, which is historical extreme wildfires reconstruction and study. And then, of course, the WG3, which is capacity building. In terms of expectations, we have a wide audience, very broad also in terms of expertise, I would say. So for you more familiar with remote sensing, probably what is going to be showed is too basic, I would say. Especially if you're aware of and have experience on remote sensing and applied to wildfire spread. For the ones that do not have any kind of experience, this might be a little bit confusing and a little bit dense, but I'll try my best to make it super light and understandable. We will not do all of the questions in the end. I will ask you to do the questions in, if I remember correctly, it's 2 periods, okay? So we'll stop first after the fundamentals of remote sensing and the satellites and products. And then on the end, when the practical example is shown, we'll stop again for questions. And please, any question is valid. There are no stupid questions, only stupid answers, okay? So go ahead. So in terms of fire spread, we can use basically, I would say 5 types of data to reconstruct fire spread. So first, what is fire spread? Fire spread is basically how a wildfire progressed in the landscape in time and space. Okay, and you have an example here of the fire progression of a specific wildfire that happened in Portugal. It's based on several polygons that are consecutive in this case and have space well defined. So where did they burn? And it has also a timestamp. So when did it burn? So this reconstruction can be made with a lot of tools. So satellite imagery, satellite hotspots. If you're not familiar with this, in about 10 minutes, I think you will. Then you have field information, which can be photos, can be videos. You have airborne footage. Again, could be so visible or thermal. It can be videos. It can be also pictures. It can be something even more, let's say, fancy, I would say, like thermal maps. But the scope of this specific reconstruction of wildfire using satellite data is, of course, satellite imagery and satellite hotspots. We will not discuss the other sources. Marcus, in the end, in the last presentation, will show you a little bit on, give you some insights on the tool that he built, and that will be able to collect field photos or videos, or even airborne photos or videos on the field. So let's focus on satellites. Basic fundamentals of remote sensing. So satellite remote sensing, or any kind of remote sensing, means that you're acquiring information about an object without being there. That's why it's remote sensing. I will focus only on the optical passive system. Okay, so passive because it requires an external energy source. And the energy source is the sun, which provides radiation to the surface. And then this surface reflects this radiation back to the satellite, to the satellite. And this radiation, as it progresses and passes the atmosphere, it's also changed by the atmosphere. And then in the end, the signal that arrives to the satellite is a mix of the reflectance on the surface of the globe, and then also of the atmosphere that is being passed through the radiation. After the satellite senses this information, it provides or it distributes that data to land stations. So this passive system, there's another important issue, especially for wildfires, is even during the night, if in certain wavelengths, which is something that if you're not familiar, you're going to be in a couple of slides. The object in the surface can have enough energy so that energy is radiated to the satellite, and that's the case of wildfires. So if you have an ongoing wildfire during the night and you have the right sensor with the right characteristics to obtain information about it, it can sense the radiation and can observe and acquire the radiation coming from or emitted by a wildfire in the thermal part of the spectrum. We'll go there in a minute. And then, of course, distribute it again. Okay, so electromagnetic spectrum in a nutshell. Basically, the electromagnetic spectrum contains all possible frequencies of the electromagnetic frequency, meaning radiation. And this spectrum goes from X-rays to the far infrared. What we can see is just this tiny part. So there's a lot going around us that we can't see, and we all can only see this part. And this is what we call the visible part of the spectrum, because it's what's visible for humans. So there's a lot going on, as you will see, in the near infrared, the thermal or mid-infrared also, and that's quite useful to get that information. Why do I say there's a lot going on? If you see, this is what we call the spectral response curves, meaning that every object reflects radiation in different ways and in different portions of the spectrum. So as you can see here, for example, healthy vegetation reflects energy in the visible this way and then has a peak of reflectance in the near infrared. Okay, so much of what's going on is here, much more activity. If you look at the burn areas and the healthy vegetation, you see that the reflectance difference in the visible, which is what we see, is very little, especially here in the red, it's almost zero. But then if you go to the near infrared, the spectral response curves are so distinct, and the way the reflectance, the magnitude of the reflectance is so distinct that we can easily distinguish burned areas from healthy vegetation looking at the near infrared. And then the opposite, similar thing occurs in the shortwave infrared, where we have a very low reflectance of healthy vegetation and then a very high reflectance of burned areas. This is the base concept of using remote sensing to classify anything on the surface, which is any object on the surface or even in the atmosphere has a specific spectral response curve, and which is a kind of a behavior to radiation, the way the radiation is reflected. And so if we can understand that and use that information to distinguish it, we might be able to classify it. So if the visible is so short, how can we see beyond the visible part of the spectrum? So this is an image of a wildfire. It was taken by a satellite, but this is basically what, if we were on top of the satellite, riding the satellite, this is what we will see looking down. As you can see, this is similar if you go to the Google Earth or Google Maps or something similar. You don't see much. You can see some smoke. You can see some vegetation, different tones of vegetation. You can see some artificial areas, some croplands, but especially the part with vegetation and even the burned area, it's not easy to distinguish. So what satellites do is basically, or any kind of remote sensing sensor, they basically read information and the energy that is being reflected in specific slices of the electromagnetic spectrum. So in this case, what we're seeing is the red band, meaning it's the reflectance in the red area of the visible spectrum. As you can see, there's not much difference. There's not much contrast in the information that is being reflected from the surface in this wavelength. However, if you go to the near infrared, this starts to get very different. So this is the part that we can't see, but the sensor can. And on board, especially the one on board Sentinel-2. And here we can start distinguishing different areas of vegetation. You can distinguish water, you can distinguish the burned area very well. Also some smoke, although the smoke is not that visible, but you can see smoke also. And other things that you were already able to see before. So the contrast between the high reflectance, for example, here in small, let's say, cloud caused by the wildfire, pyrocumulus, and the low part of the reflectance of the burned area or water are clearly distinguishable in this near infrared band or reflectance. And then the sphere, so the shortwave infrared, so moving a little bit further on the electromagnetic spectrum. What you see here is basically the shortwave infrared is closer to the thermal part of the spectrum, meaning that you can start seeing the active flame, the active part of the wildfire, what has active flames. And you can see this in a bright color, meaning that it's reflecting a lot in the shortwave infrared. And what for me is very interesting in this image is that if you go back and you see the burned area, which is pitch black, here it's almost invisible. Whereas the opposite also occurs regarding the active areas. They are almost invisible here, and then they're clearly visible here. So this is how we can see beyond the visible part of the spectrum. And this is, I mean, this is where all the fun is in using satellite data for any kind of application. It's using information beyond the visible part. So if we have different bands, how can we then mix this all together and see this different information? What's in the infrared, what's in the sphere? Do we have to see it one by one, or can we use something a little bit more practical? Yes, we can. It's called color composites. Color composites are basically, what we're saying is that any image can be a combination of red, green, and blue. So what we see here is a combination of red, green, and blue, in which the red was assigned to the reflectance coming out of the red area of the spectrum. The green was assigned to the green area, and the blue assigned to the blue area. And you might say, well, that's basic. It is. What's really nice about this is that you can switch the order of the bands, and you can put there other information. So if you do this, which is basically switching the orders of the bands and putting here information that your eye can see, but comes from a part of the spectrum that your eye cannot see, you get what it's called a false color composite. And now we're mixing the red, which is part of the visible, and then two bands or reflectance in two areas of the spectrum that are not visible to the human eye, which is the near infrared and the shortwave infrared. And you get this very nice color composite, which is called false color composite. False because you are not, the information that you are seeing is not from the visible part of the spectrum. So here you can distinguish a lot of things: water, active flames, burned area, small pyrocumulus, which could be also, it would be similar if you had a cloud in this image. Smoke, although you might you might notice that the smoke is kind of transparent. Let me go back. Look at the visible image. This is what you see in the visible. The smoke is thick, and here it's not. And this is something that might seem a detail, but I think it's important for you to understand. And it might be very useful also when looking at wildfires where there's a lot of smoke. This is not one of these cases, okay? There are images that are filled with smoke, and it's easy to understand exactly what's beneath. If you use wavelengths that are higher wavelengths, so high wavelengths that are far away from the visible, so the near, the SWIR, the thermal, etc., the smoke becomes more or less transparent. Why? Because the reflectance of smoke is very big in the visible part of the spectrum, and it's very low in the near infrared, short infrared, wave infrared, and thermal infrared. So because that reflectance is very low, if you're using channels that where the reflectance is low, it's going to be more or less transparent in the images, and this can be a very handy feature. So you can also see vegetation and, let's say, different tones of vegetation, healthier vegetation in green and bright green, and then less healthy vegetation in dark green. Some sparse vegetation here, this color, and then artificial areas and croplands. Well, a mix of croplands with different states and different types of vegetation also. Okay, so the fundamentals of remote sensing, it's this in a nutshell. Now let's go to satellites and products. Well, before the video, we have two types of satellites, geostationary and polar orbiting. You don't need to know much about them. What you need to know is there are some very, very large differences in both of them. So polar orbit means that they basically fly around the Earth, crossing the poles. So, and this is the case of the most known satellites like MODIS, like VIRS. Well, VIRS is not a satellite; it's the NPP or whatever. NOAA 20, etc. Sentinel, Landsat. Those are polar orbiting, meaning that they pass through your area. They have to contour the globe entirely until they reach again your area. And then the geostationary satellites. And as the name says, they're stopped, they're stuck. Well, they're not actually stopped. They basically follow the rotation of the Earth, but they're always in the equator. So they're always looking at the same area, and they're not moving around, observing different areas. This is a very short video that will basically show how it works. So polar orbiting, you see the slices are basically the area that they're covering, and then the geostationary satellites are basically in the same place, always looking at the same area of the globe. Okay, usually this is not a rule, but usually the geostationary satellites have a very high acquisition frequency. That's more or less a rule, but the resolution, the spatial resolution, is low. And then the polar orbiting sensors usually have higher resolution, but of course the acquisition frequency is lower, again, because they have to, contour the Earth all over again until they reach to your area. Some take more time, some take less time. Oops, sorry. Okay, so, sorry. There are, I would say, a big trade-off there are many satellites available. So these ones that I'm showing here, just a tiny fraction of the satellites that are available. I would say that for fire spread reconstruction, they are probably the most relevant now. Although if you go to the past, you will have other satellites that were also relevant. And in the future, and I'm thinking about, for example, the Meteosat third generation, which is already flying. that one will be very relevant as well. And I'm not including here, for example, GOES satellites, which are covering, or Imawari satellites that are covering other parts of the globe. I'm thinking about Europe. Anyway, this is not an exhaustive list. The idea here is for you to understand the trade-offs between the satellites. And there is a big trade-off, which is usually spatial resolution increases, temporal frequency decreases. Meaning that if you have very, very high spatial resolution, you cannot have that every 10 minutes. You will have that, well, it's variable, but you will have that in many days. Maybe daily, maybe more than one day. So if you go to the non-commercial satellites, and let's start with Landsat and Sentinel-2, these have resolutions of 10, 30, 60 meters, and they have a typical frequency of around 10 days. Some of you will say, oh, well, this is not true, because Sentinel-2 I have every 5 days. Yes, because they combine two satellites, and they're off phase, let's say. So the same satellite revisits the same part of the globe every 10 days, but because they are two and they're off phase, let's say, they have a combined frequency of 5 days. Anyway, one satellite takes 10 days to revisit the same area, but you can get very good resolution between 10 and, I think it's between 10 and 60. The same thing with Landsat 8 and 9 and the other Landsats that you had in the past. And as you move forward and you decrease spatial resolution, and I'm talking about moderate sensors like VIRS, ProbaV, Sentinel-3, OLSC from ESA, you will start having special temporal frequencies that are in the order of a day. Some of them less than a day, some of them more than a day. It really depends on the sensor itself. Then when you go to the moderate and the coarse ones, you start having a much higher frequency. So if you're thinking about Sentinel-3 and MODIS, and also VIRS here includes, you can have observations about 2 to 4 times per day on average of the same place. So your area of interest is visualized, observed by these satellites on average 2 to 4 times per day. But they come with a cost, which is the spatial resolution is on average lower. Okay. Then if you go to the geostationary, because they're in the same place all of the time, their temporal frequency is 10 to 15 minutes, so it's super high. But that comes with the cost of low resolution. And the Meteosat second generation, which is the MSG, has around 4 kilometers of spatial resolution. The new one, I think, will have around 1. GOES, for example, is kind of the one of the many brothers in flying over America, so North and South America. It has a spatial resolution, I think, between 1 and 2. It depends on the GOES satellite. So as you can see, there are a lot of, let's say, toys to play in terms of satellites, but they have their own characteristics, and they have this trade-off between spatial resolution. Of course, we would love to have Sentinel to 10-meter resolution, maybe even higher, every day or every more than once per day, but that's not practical in terms of amount of data that is processed at the moment. So I'm not going to go through this table. This is just a list of the most relevant satellites and bunch of characteristics like the number of satellites and instruments, spatial resolution, frequency, meaning the revisiting frequency, number of spectral bands, and responsible. It's for you to use if you see anything that might be updated. These things are changing. For example, VIRS just launched a new satellite, so I had to update that yesterday, which is aboard the NOAA 21. If you find, I think that this will be useful as a kind of a side note. If you find any error here or something that needs to be updated, please let me know and I will do. So to wrap this up, I will just talk about 5 different notes that I believe that are important, although we do not have time in this specific webinar to go into detail. So it's just to make you aware of this and just to put this information in the back of your head. And if you will use satellite data, maybe you will remember this. So first, satellites have different bands, meaning that they can look at different slices of the electromagnetic spectrum. Not only they have different bands, but they have different orders, meaning that, for example, the near-infrared band in Sentinel-2 is called band 8, but in MODIS it's called band 2, and in Landsat 8 it's band 5. So every time you want to look at the near-infrared information for your study region or your operating region, you need to look at this. You need to start, well, just Google it, just put Sentinel-2 bands, and you will understand which one is in the near-infrared, okay, or Landsat or MODIS. So that's important. Don't use band 8 in Sentinel-2 and then go and use band 8 in Landsat 8. Results will be dramatically different. Second thing, whenever possible, use reflectances that have atmospheric correction. Okay, this is a very technical remote sensing aspect. I will not go into details. I will just let you know that in Annex 2, which is in this presentation, and I'm not going to show it, it's going to be shared, you will have some details about this, okay? Same thing with the third aspect, which is the pixel size is not the same between satellites, and that was already clear in the previous slides, but even inside the same satellite image, so image, for example, that is taken today over my study region, for example, the pixels will not have the same size. So, and this is particularly true for satellites flying higher let's say in altitude. Pixel deformation increases with viewing angle, meaning that as you start to get oblique angles and start having higher viewing geometry, the pixels start to get bigger. Okay, very technical. Again, more information in Annex 3. Maybe you'll use remote sensing for your entire life without even having to bother with this. If you're using Sentinel-2 or Landsat, this is not a big issue. So, fourth important note, satellites have different lifetimes, time spans, whatever you want to call it, meaning that, well, Sentinel-2, one of them started in 2016, for example. MODIS has been around since, one of them since 2000, the other one since 2002. They have different time spans. Depending on what you want to do and the information that you want to collect, you need to check what were the satellites that were available in that specific time, okay? So VIIRS, for example, only started in 2012. If you're trying to reconstruct fires using VIIRS data, for a fire that occurred in 2001, it won't be possible. That's it. The fifth is that all satellites record the time of acquisition in UTC time. And this is important because we have a lot of time zones in this specific webinar. So it's not your local time, it's UTC time. Okay, most relevant products for fire spread mapping, not for fire study in general, but for fire spread mapping. Reflectance composites, we already spoke about this. It's a very quick and easy way to get information about what's going on the surface. And then one especially relevant product are the so-called thermal anomalies or hotspots. What are the hotspots? So basically, this is not an image. This is well, actually, it can also come in an image format, but most common format is a vector, a shapefile, a point shapefile, or a point vector file. Every point has, of course, the space, X and Y, and has the time it was detected. It also has something usually calculated, which is the quantitative power. It's a measure of how much energy is being released at that specific point. That point is only triggered when there's a thermal anomaly, meaning it's hotter than the surroundings. And this is especially interesting for wildfires because usually wildfires are extremely hot, so they're hotter than the rest of the surface. And when the satellite passes, it triggers the thermal reflectance, and basically this product says, okay, these points are probably being crossed by a fire because they're extremely hot. So this is more or less how it works. As I said, it identifies the center coordinate of a pixel where part of the fire is burning. And this is an example from NASA, which I think it's quite helpful. And then the location, date and time are recorded. So, for example, this is a ground observation. This is what is really. This is the grid. This is what is really happening on the surface. Okay, so we have a small fire covering this pixel, which is what this is the pixel of virs, for example. And so the output will be, okay, this point specifically here is burning. We don't know if the fire is here or in this corner, okay? Or in this corner or in this corner. What we know is that this area is burning, okay? So don't be fooled by the point and thinking that the point is very precise. It's not. It's burning in any part of the pixel, okay? This is another example with two. Again, we're not able to say there's one here and there's one here. We're able to say is, okay, this specific cell is burning or is probably burning. And then this example means that there's either a big fire in the center of the grid, and all four locations are triggered, they're saturated, or all of the grid cells are burning. So this is basically how these hotspot products works. Okay, so let's go for questions. I don't want to move on without clarifying if there are doubts in the fundamentals of remote sensing about the satellites or the products. Next, we're going to have a practical example. So if we can clarify all of the more theoretical part, I think it would be a good moment now. Don't be shy. You can maybe, yeah, go for me.
Hey, good morning, Akli. I hope you're doing good. So I have a very quick
Hi, Fermin.
question. What do you think about the SDG SAT Chinese products? Did you ever use them?
Tell me the acronym, please. SDG.
SDG SAT 1.
Okay.
I will post the link here on the chat so you can.
So you can understand by my reaction that I don't know the satellite. I think
I am not a remote.
Yeah, go ahead, Fermin. Go ahead.
No, I'm not a remote sensing expert. It's just something I found the other day, and I was just curious.
I'll send you a feedback by email. I think that's easier. The list that I created here is not exhaustive, and it will be probably very much outdated in next 6 months or one year, because these things are constantly evolving. They are extremely relevant satellites. For example, the geostationary satellites are a good example because they are stuck in the same place the entire time. You have MSG in 2 locations of the world, but you have GOES satellites in the entire North America, and you have Imawari satellite in Australia, Japan, I think also Southeast Asia. So there might be there are for sure relevant satellites that I did not include here, okay, in the list. Anyway, this should get you started in almost any part of the globe, with the exception of the geostationary satellites, meaning that Sentinel-2, Landsat, Sentinel-3, MODIS, VIRS, they're covering the entire globe, and some of them more than once per day. This should be enough to get you started. There might be relevant ones. We also have some Portuguese satellites. I never use them. If you can complement that with your analysis with Portuguese satellites or Chinese satellites or Australian satellites, yeah, that will make probably things you know, clearer, and you'll have a wider view of the topic that you're trying to analyze. So again, the list was not exhaustive, but I can provide you some feedback on this. If it's let's say suitable or not for fire spread, for fire mapping.
Thank you.
Thank you.
I have a question.
I have difficulties in managing the questions, so I would say that if Liliana, maybe you can check this, or Theodore.
I wanted to jump in. If you have questions, please raise your hand. And I sorted you by raising hands.
I think Bezarevich.
Yes, Branko. If you could please introduce yourself.
Branko. Okay.
Yeah. Introduce yourself and say the question.
Yes, Branko Bezarevich, National Park Tara, Serbia. What coordinate reference system would be most appropriate to use for this reconstruction?
Okay. It might look like a very technical question, but this is an important question. So I'm not sure if all the satellites come with the same coordinate system. I honestly don't know. I mean, there are some options, and you will see this afterwards, where you can even select which is the coordinate system the satellite that is being outputted. I think there's one very important key aspect in the coordinate system. Always use a metric coordinate system, because mainly of two things. Projected metric coordinate systems allow you to calculate area in hectares or square kilometers, and if you use a geographical coordinate system, it won't allow you to do that. So areas in those are calculated in degrees. You don't want that for fire spread mapping, and especially for fire behavior metrics. The other aspect is the distance, which is similar to the area. When you're calculating distance in an angular coordinate system, it will give you distance in degrees. So the other one was, so distance are in degrees, yeah, exactly. The other one, the area was in square degrees. So if you're calculating, for example, the rate of spread, you cannot calculate, it doesn't make sense to say half degree per hour, okay? So it makes sense to say 1,000 meters per hour, for example. So yes, use a metric coordinate system. Use the one that is, so if you're in Europe, you can use the European one, which I don't remember right now which one is it, but it's the standard one, at TRS something. But if you want, you can also use a coordinate UTM coordinate system for your country. The most important thing is, if you're only doing, my sound is unstable. I don't know, is it? Liliana, it's fine. Okay.
Yeah, it's fine. I'm losing you a little bit, but I think my microphone is also, my internet is also.
Okay, I can change the microphone maybe.
Yeah, I think it's not due to microphone, maybe due to internet connection, but I think it's manageable. Yeah, it's okay.
So, yeah, the coordinate system itself is not really the most relevant thing. The most relevant thing is use a projected coordinate system in meters, not in degrees.
Thank you very much. It was very clear.
Thank you, Marco.
Thank
there was another raised hand.
Yes, there was another raised hand. Savas Gakontas. I'm not sure I'm pronouncing it.
Hello, thank you very much. Savas Ganton is my name, from the University of Cambridge. I hope you can hear me.
Yes, we do. Go ahead, Savas.
Thank you. So the question is, when a satellite like Sentinel-2, for example, passes over an area, does the satellite take only one picture of a particular pixel, or does it take two or more pixels with some small time difference?
The same pixel is only viewed once every time the satellite passes, but it's viewed once in multiple dimensions, meaning that I'm looking at one specific, I'm overpassing, and I'm looking at one specific pixel, and I'm taking information about the reflectance in the blue band, in the green band, in the red band, etc., etc., etc. But to the best of my knowledge, yes, the information in that pixel is only viewed once. This should be double checked. This should be double checked because I remember there were satellites. I never gave them that much attention to this, but there were some satellites that saw the same area with. So the same pixel was viewed twice with different viewing geometries, and that differences in view geometries were useful to have a kind of a 3D perspective. I don't think that's the case of Sentinel. I'm almost sure it's not, but I'm not completely sure. And I don't exactly remember which satellites did this, of visualizing the same area, the same pixel with a difference of, I would say, minutes, probably, maybe even less than a minute. But no, Sentinel-2, it's bam, an image, that specific pixel with multiple layers of information, meaning different reflectances, and that's it. Don't forget, the bands in Sentinel-2 have different spatial resolutions. So the higher resolution bands are 10 meters, but then if you go to, I think it's, for example, shortwave infrared, it's 20 meters, meaning that the same pixel is not a pixel in all of the bands. Not the same pixel in all of the bands. Okay, so it's not sure if there's a resampling process in the middle or if the sensor is just different. Okay.
Thank you very much. This was very clear.
Thank you, Sarah.
Yes, actually, we have a question in the chat, if you can address it also.
Okay.
Can you see the question, or do you want me to read it?
No, I can see. I think I can see. It's from Jürgen Rombo, right?
Yes, right.
If I understand, I'll read it out loud. If I understand well, the limitation to have higher resolution data at a higher frequency is the amount of data to process. The way to overcome this is to have more satellites orbiting the Earth in phase. Oh, that's a super technical question, but a very good one. I am assuming. So I come more from the application side, not from the development side of satellites. So I am guessing that the idea that I have is that the biggest limitation is the flux of information and how to store it. If you had more satellites flying, you would increase the amount of information. There's another issue that is relevant. It's not only the amount of information that is being stored on the land surface, so not on the satellite, but it's also the information that is being also stored temporarily in the satellite, meaning that I think most satellites work like this. They capture the information, they store it on board. I think some of them even process it on board. Again, this is super technical. Usually don't get there. And then once they do that, they have to discharge it and send the information somewhere. So even the internal amount, internal storage could be a problem. I'm not sure if all of the satellites have the capacity to store that information. Another issue is physics. So if you have a polar orbiting sensor, well, it has to run across the Earth, so it takes time, and it's not possible to have the same satellite passing in the same area every hour. That specific issue, yes, could be solved. I would say so, although again, I am not, let's say, a remote sensing developer. That specific issue could be solved probably with having more satellites orbiting the Earth in phase, yes. But again, we should be aware of the amount of information being generated. I hope I was clear. Any other questions? Go ahead, then.
Hey, Akli, good to see you again.
Hi.
My question is perhaps similar to the ones before, more towards commercial constellations. Have you used any commercial data providers, for example, Planet Labs or Aurora Tech? They are both providers of, high resolution and much higher spatial resolution, sort of temporal and spatial. Curious what your experience there has been.
I haven't. I know Aurora Tech. I know part of what they do. But the other name that you mentioned, I never heard of it. So commercial satellites, they do have, I mean, if you have several birds of the air looking at your surface of interest, I mean, you have, and having the right instruments to do that. So for example, if they don't have a thermal infrared, a thermal band, it's difficult to map hotspots, for example. So if they have the right characteristics, and if possible, if they have, like the previous question, they have different, they have lags between them, so they're not in phase, or they're in phase, sorry. If that happens, that will provide you always with more information, and that would be helpful. So I am completely, I totally support using more information, commercial and non-commercial, to specifically map fire spread. I've never used it just because it's commercial and it's paid. That's it. But if it wasn't, I would surely use it. So the objective of this specific workshop was to give you freely available tools to map fire spread. We would probably need to ask someone else to give you non-freely available tools to map fire spread, and that would probably come as a product, and that would be very interesting also. But that's not the scope of the workshop. And then there was another issue that I just forgot. Yeah, I don't remember. But yeah, I think that covers it more or less.
Thanks.
I don't see any other hands raised.
Okay.
Yeah, if there are no more questions, maybe we can move on to the practical part.
Okay, let's move on then. Okay, very useful and practical links. These will be, I mean, I use them all the time, and they're. If you're like me and you started using this several years ago, you will acknowledge that these three sites, and there are many sites with satellite data, there are tons of them, but you will acknowledge the development and evolution that we've had in the last years. So I'm highlighting these three links, which is Sentinel EO browser, Worldview, which is from NASA, and the Fire Information for Resource Management System, which is called FIRMS, and you probably know it by this acronym. This is remote sensing of data available at the distance of a click for anyone that does not have experience in remote sensing, which is great. The case study will be, so we will reconstruct the fire spread of a specific wildfire that happened in Portugal in 2022, called the Serra da Estrela wildfire, at least I call it like that. It's called Covilhã Roxo, for those most familiar with. It started on August 6th of 2022 and ended on 17th of August. It had some small minor rekindles afterwards, but let's consider that the last relevant spread was on the 17th of August. It burned almost 25,000 hectares. And of course, I brought you an example where satellite data fits very well and is very handy. Okay. I will start by giving you a notice, a warning, let's say, when you use this kind of data, is that this example might look very nice and very fancy, but I don't want you to be disappointed if your wildfires, for example, are occurring. And I now remember what I wanted to tell you then, which is the different satellites have different observation moments. Okay, so geostationary are looking at the surface every 15 minutes. So let's say it's the entire day. But when we're talking about Sentinel-2, the observation is around 11, 12 UTC. So there's not only the frequencies every 5 days, it's a very specific observation in that window. When you're thinking about, I'm not going to tell you all of the windows, but the windows are limited during the day, very limited. And they're usually around 11, 12, 13, 14 UTC is the first period. And then the ones that overpass during the night, because again, remember, thermal information, there is thermal information that can be visible by the satellite during the night. Those pass around 10 p.m., 11 p.m. Maurice Terra, and then the other ones, Veers, Modis Aqua, around 2 a.m. more or less. Okay, so if you do the math, you will see that between, let's say, 2 a.m. and 2 p.m. there's a 12-hour gap. Okay, so we can have easily 10 to 12 hours without any satellite observation. So going back to your question then, and I'm happy that I remembered, if we have other satellites that are able to visualize what happens in between, that's extremely useful. And that's something that, at least in our country, we were able to, let's say, limit the effect by having basically airplanes flying with thermal sensors. But if you're from a country where you don't, well, even in our country, if a specific fire did not have an airplane flying, you won't have any information between 2 p.m. and 2 a.m. So this leaves a big gap in terms of information. What are the problems? And this is going back to my warning. And I don't want you to get disappointed when you're doing this for a specific fire back home. If all of the action occurs between 4 p.m. and 8 p.m., you're not going to see anything in the satellite. Okay, you're going to see, okay, no fire. Second image, oh, everything is burned. So be aware that this works really well in a long-lasting multi-day wildfire like this one. It does not work well for very fast fires that occur in between the time windows of satellite observations. Okay, we should have, let's say, an improvement with the third generation Meteosat that is going to be working hopefully this year or in the beginning of next one. But still, the resolution of those satellites is still coarse. So if you have a fast but relatively small, fast spreading wildfire, probably remote sensing is not the tool for you. It could be useful to map the burn perimeter, but it's not going to be useful to map the spread. Okay. So let's move on. Step one, and this is going to be like a recipe for making a cake. But of course, like in TV shows where they do cakes, the cake ends up done in the end. So you don't have to wait for the time that it's in the oven. Otherwise, it's not practical. So first step, define a timeline. Okay, and defining a timeline means when did it start, when did it end? This is going to be our window, or time window. So I know that this fire started at this hour, not because of satellites, but because of fire service, okay, or the Forest Service. So official data tells me that this fire started on the 6th of August at 2 a.m. in the morning. And then I know the fire finished at or ended at the 17th. Official data is not really useful usually to know what is the exact end of the active fire spread, because the end date of official data usually is concerns the date where the fire was considered extinct. Okay, this depends a little bit on between countries and service, and even between fires. But if the head of the fire stopped progressing, no one was going to register that as the end date. Okay, and you should be aware of that. So once we have the timeline, second step is isolate the final burn perimeter. Some of you will say, well, this is very easy. I have official data that gives me the perimeter. That's great. If you're lucky, that's really good. However, be aware that sometimes there are errors in the perimeters. For example, multiple ignitions that coalesce and join, or not coalesce, but ignition fires that are close by and they're independent fires, and that they occurred between two different images. That happens. But anyway, if you're not lucky to have this information, you can isolate the final burn perimeter by doing what? Go and this is image taken from Sentinel EO browser. One important aspect that I forgot to mention, in Annex, I think it's 5 of this presentation, you have a kind of recipe to download the image from Sentinel EO browser. It's super simple. You probably won't need the recipe, but the recipe is there, and you can download the images. So once you download the images, you download one before the ignition and after the end of the fire. So as you can see, a lot happened between one and the other. Why do we take one before and one after? One after is for the obvious reason, and the one before is, as you can see, if you did not know that these fires were, especially this one, look at this one here, it merged, right? Actually, one of the fronts stopped in a previously burned area. So you need to remove this part from the final perimeter, okay? Which should look something like this. And see, this part is from a different fire. So the important thing here is let's isolate the final burn perimeter and move on. This is going to be our basis. Okay, so before we go to this complicated slide, let me go back. The strategy from this moment onwards is simple. Strategy is we are going back to the metaphor of cakes. We have a cake. The cake is the perimeter. And what we're going to do is we're going to cut it in slices. Okay? And we're not going to cut it in slices, all of them with the same size. We're going to start cutting big chunks. And then for each chunk, if we have more information, we cut it in 2 pieces, in 3 pieces, in slim slices or big slices. Okay? But the idea is we start from the cake, let's say, and then we start cutting the slices. Okay, 3, locate all available satellite images and hotspots in the timeline. So again, this is the start, this is the end. All of these mark a new day. All of these lines mark a new day. So this is, again, your timeline. We'll be using this throughout the presentation. And basically what this shows is that we have first level, which is high resolution data, Sentinel-2 Landsat. We have an intermediate level, which is imagery, which is from moderate to low resolution satellites, Sentinel-3, VIIRS, MODIS. And then we have a third layer, which is the hotspots, which come from MODIS, VIIRS, mostly. Those are the most, I would say, most relevant, MODIS and VIIRS. So, step 4, use the first layer. Let's break the cake in, let's say, how many pieces? 4 pieces. 5 pieces, sorry. 5 pieces. And the 5 pieces are basically, we went to Sentinel EO browser and we downloaded I downloaded the Sentinel, Sentinel-2 and Landsat. This is Sentinel, this is Landsat. High resolution images that were available in my time frame. Okay, so the beginning, then somewhere in the middle, and then in the end, as you can see, it's filled with clouds, but it's still useful because we can see the active part was here around this part, and you can still see parts that were active. So this image is super, super useful, okay? Even with clouds, it can provide some added value. Okay, so once we do that, and as I told you, now we break one piece here, another piece here. Oops, sorry. Presentation isn't fast. Sorry. It's stuck. Okay. Sorry for that. So we're breaking it from ignition to the first image. There's one progression, one piece. From the second image to the first image to the second, it's a second piece. Okay, 3 pieces, 4 pieces, 5 pieces, and then 6 pieces. So between this and the end. Okay, just by looking at satellite, high resolution satellite image freely available, you can divide the burn perimeter in 5 pieces. And most importantly, every time you break in a piece, you know that you don't know exactly when it started, and this is something that we need to be very cautious, okay? But you do know when it ended. So meaning that if the fire progression is still active, and most of these here have active parts, you can say that the fire was active at that specific time of the satellite overpass, okay? And that's very important, because that will be your progression date and time. Okay. I apologize again for the presentation being super slow. I think it's too heavy. Okay, so once we use that information, here it is, 6 pieces of progressions. We just started dividing the coarse chunks of our perimeter. Next step, break the final perimeter in intermediate perimeters using moderate resolution imagery. I'm not using here MODIs or VIIRs. You can go to Worldview and download the data. It's super, super easy. I'm using Sentinel-3. Sentinel-3 is a bit more tricky. That's why I have an annex for that, to create these composites. And the composites look different. Not only they look coarser, because the imagery is coarser. The resolution is not 10 or 20 meters, it's 300 meters, okay? So this is why it doesn't look so appealing, let's say. Also, the colors are different. The colors are different because we're using a false color composite that is also different from Sentinel-2. Why? Because the bands in Sentinel-3 are not exactly the same available in Sentinel-3 OLCI, which is one specific instrument of Sentinel-3. So again, we divide this in different pieces. So we start mapping the progressions. Sorry, the presentation is super slow. Okay, here it is. And so from this 6 pieces, we divide this into basically daily fire progressions, which is already extremely useful. Okay. To this fire progressions, I just added, I forgot to mention, I added the ignition, and the ignition was reported. Okay, so it does not come from satellite. All of the rest comes. That's it. So we already have around the cake that has around 10 pieces. Sorry. Step 6, break the intermediate perimeters using thermal hotspots. And I'm going to use only VIIRs, 375 meter hotspots. You can download this very easily, very quickly from firms. There are other places you can download, maybe more stable versions. That's up to you. The archive download in firms works just fine. So as you can see from the figure on the left, this is a different ballgame. We have here around 2 to 4 observations per day with all of the VIIR satellites. So the VIRS is a sensor, is on board on 3 satellites. So we have 3 different observations. At this specific time, we only had 2 satellites. So it means that we have the same satellite coming on early afternoon or around noon and then around 2 a.m. multiplied by 2 satellites, meaning that we have 4 viewing windows, okay, viewing moments during the day. And as you can see, this provides very rich information in terms of what was the spatial and temporal spread pattern of the wildfire. So some things that you need to take into account where you're using these thermal hotspots. So we're not dealing with images again. We're talking about points. So you need to make an inference of what burned in the points. Okay, you don't have an area. You need to be careful with resolution. So you will find some hotspots outside of your burned area. This is normal for several reasons. One of the reasons is, for example, here, as you can see, these hotspots are outside of the area. And this happens because of what? First, the resolution is not very high. It's at the best case scenario, 375 meters. But remember, one important note is that the pixels get bigger and bigger as you start looking them with the oblique viewing geometry. So you might find here pixels with 450, 500 meters of resolution. So this explains why, is one of the main reason why there are pixels, there are hotspots outside of the burn area. The second reason is VIR specifically has a tendency to, when the plumes are very hot, it has a tendency to go after the plume and not the burn area. Okay, so the heat being dissipated by the plume is sometimes captured by the VIR hotspot. It's not super common, but it does occur. Okay, so always integrate the hotspots according to the previous progression final perimeter, meaning that if VIRS is telling you this part here burn or here it burned, I mean, ignore it in the sense that you know that it didn't burn because you have the final perimeter. And you also have the progression that occurred afterwards because we did the daily progressions, okay? So these will be your constraints. You never map a progression outside of what you know that burned. It is, but yeah, that's the beauty of merging area with, imagery with hotspots. Only use relevant observations that have significant widespread, fire spread, sorry. This sometimes happens, for example, between 1:30 and 3 a.m. It's these black dots, you can't really distinguish the difference. But what happened here is that, as in many fires, and I would say across the globe, specifically in Portugal, is that during nighttime, things get really, really calm in most of the wildfires. So between 1 a.m. and 3 a.m., there is no significant widespread fire spread. So don't use the 3 a.m., use the 1 a.m., okay? Meaning that if there is no significant widespread, you know that the fire reached a certain area around 1:30. And you say, okay, the progression is this area at 1:30 in the morning. Don't say it's 3 in the morning, because if you do that, you're going to add 1 hour and a half or 2 hours. And when you're calculating the rate of spread, for example, you're going to underestimate the rate of spread, meaning that the same distance is going to be covered in a higher amount of time. And you don't want to do that. Then, if applicable, advance the date and time of previous progressions, meaning that if you have, let's go to this example, the 7th. Okay, I have an example. I just remembered. Here it is. So this progression here, specifically this dark brown, this light brown, was was defined using a Sentinel-2 image of 11:30 a.m. And the previous progression was this one here, and it was taken from a Sentinel-3 image. So we might say that the fire spread came from here to here, and it took more or less 24 hours. And this is, yeah, it is right, but a lot of things happen in the middle. What we know in the middle is that around 1:30 a.m., these black dots, which are Veer's hotspot, show that the fire was around here, okay? Around here. So the flanks were already, let's say, covered, burned, and the front was almost here. It wasn't here, but it was here. So what you do is you're going to cut this progression in two and say, okay, in fact, from here to here, it didn't take 24 hours. It took from here to here around 12, and then from here to here, other 12. And this makes a big difference when you're calculating rate of spread. If you do from here to here, you're going to calculate an average, very underestimated rate of spread. Whereas if you can break this in 2 or 3 or 4 or 5, you're going to have a much accurate rate of spread, which will be up and down probably. This is not the best example of why you should advance the date and time of progressions. But let me give you an example. If these points here were already covering the entire polygon that you know that it burned at 11:30, you should say, okay, well, in fact, this didn't burn at 11:30, it burned at 1:30. So advancing in about 10 hours, the fire progression, okay? And this will mean that you will reduce significantly the underestimation of rate of spread calculation, okay? Again, it's always about merging the different sources of data. This is the big trick. It's images from several sensors and then hotspots from the available sensors, but I think Veer's is the best one, and merge them as best as you can, because they tell different stories. They have different limitations and advantages, and they tell different stories. If you merge them, they're stronger than when they're looked individually. Okay, I cheated here, okay? Warning. This, if you apply the hotspot data, does not lead to this. I had a problem yesterday and I couldn't give you the exact shapefile. So this is the final shapefile, but has other data available, okay? It's airborne data, field data. What I wanted to show you is that you can move from around 10 progressions, so 10 pieces of the cake, to, I would say, at least 20 when you add the thermal hotspots from Veer's, okay? I'm sorry I wasn't able, I had a strange error with QGIS, but the idea is not to provide you the shapefile, the final shapefile. The idea is to show you we're cutting the layers of the cake in thinner pieces. That's the most important thing, okay? So remember the timeline. We started with the start and end only. We added the dark red ones, which were very high resolution imagery. We then added the red ones, which were the moderate to low resolution imagery. In this case, we only used Sentinel, but I mean, it is useful to look at MODI's or Veer's data, but they're coarser, okay? So bear in mind that. And then in the end, we added the orange ones, which are the thermal hotspots. So in a more than 10-day fire, you have enough information almost throughout the entire fire to provide a good reconstruction of fire spread. So once you do that, and before that, I think it's very important to highlight one thing again. To calculate any fire behavior descriptor, you need to know when, very well, with the best accurate possible. You need to know when it started. So basically, think about this as a race. If you only look at when an athlete got to the finishing line and say, okay, he finished at this time, you cannot calculate his speed because you don't know when he started running. This looks obvious, but this is extremely important when you're calculating fire behavior descriptors, especially, well, using satellite data or airborne or field data, whatever. It's always the most tricky part. It's to know when it started and when it ended. When you have an ignition, it's more or less easy. Okay, this was the time it was reported, and then I have satellite image 10 hours later. Okay, this is the end and start and the end. But that's not always the case. Sometimes you have fires that go, they advance, they stop, they advance, they stop. And so knowing the timing where, let's say, the onset of, for example, a reactivation, it's very important to calculate, and this fire was one of these cases. It's very important to calculate the fire spread rate, for example. So the speed at which the fire progressed. You need to have an idea when it started and when it ended. All of the work that we've shown here is mostly to understand when it stopped, although with images that show some images that show active fire behavior, so active flames, you know that the next progression, the start was the previous one where you had the active part, okay? So it was active 12 hours ago. So if it reaches a certain area 12 hours later, I think I can calculate the rate of spread, okay? But if you do not have an image, a previous image saying, okay, this was active for several hours, at this specific hour, it's more difficult and it's more tricky and less accurate probably to calculate fire behavior descriptors. Okay, a very easy, very simple, very easy way to calculate two descriptors. And I will focus here on the rate of spread. So these are two consecutive polygons, progression polygons, one here and then the other one here. How do we calculate rate of spread? It's basically, and the other polygon here. So it's the terrain distance, not the Euclidean distance, okay? So it's the distance covered by the fire on the ground from this point to the outermost point. So it's this one. This is the head rate of spread. This is the most common fire spread descriptor. So the same thing goes here. You know when this polygon started or finished, which means it's the start from the next one, if that's the best available you have, and you know when this one finished. So you know the delta t, which is the time, and then you know from here to here you have a distance. Distance divided by time equals to rate of spread. Okay? And looking at the amount of data that I showed you previously, it allows you to do this, basically, to calculate the rate of spread. You can calculate the growth rate, which is basically the area of a polygon, or several polygons, if that's the case, divided by the amount of time, let's say, beneath the generation of that progression. And you can calculate the growth rate. So how many hectares per hour did this fire spread? So once you have that, you can have a very clear image of what was initially just a burned area. You can see that there were ups and downs in the fire behavior. And it actually had something that is very interesting. A 3-day period, an almost 3-day period where there was no fire spread. So the fire was, you know, sleeping, let's say, and then reactivated on the 15th. And this is the kind of things that if you were to make the mistake of calculating an average rate of spread, you would miss all of this. And you probably have a very low rate of spread because you would average it, okay? So again, this shows the importance not only of having very detailed and the potential of having satellite data to provide this detailed you know, framing of the fire, but also, and I need to stress this again, also the relevance of clearly defining when it started and when it finished the progression, okay? Okay, last slide, well, almost the last slide, take home message. I think it's more or less clear that fire spread can be reconstructed using freely available and easy to use satellite data that can be complemented with, of course, commercial data and or even maybe not so freely available data. The approach presented, at least the one that I presented here, can be applied in any part of the globe. Sentinel-3, MODIS, VIIRS, Sentinel-2 and Landsat 8 and 9 cover the entire globe, so we can map fire spread in China or in Australia or in Chile. Okay. Very, very, very important take-home message. Please converge as much sources of evidence possible. Okay. Just because you have a very nice image of Sentinel-2 doesn't mean that you shouldn't look at what happened in VIIRS. What are the hotspots in VIIRS? Again, because they can show you that this area had already burned by completely 12 hours before. That's very relevant. But also use other Sentinel-3 images, MODIS, VIIRS. Sometimes they're very useful just to say, okay, I have more than one source saying the same thing, so I can trust this. That's very important, and I would say that's the key. That's the secret of all of this. As you saw, I didn't show you any kind of fancy algorithms, and they're useful, but I didn't show any kind of fancy algorithms. All of the progressions were made handmade, which is a pain, but it were all handmade. And fancier algorithms will be welcome, of course, and they are needed. But all of this was done without any kind of fancy things. Just freely available, easy to use satellite data, convergence of multiple sources, and then dividing the big cake into smaller pieces. Be careful with limitations of satellite data and products. They are not reality, so they're always observations / estimations of what's going on the surface. Be very cautious with that. Don't ever mistake that with reality. And remember, they have limitations of clouds, smoke. It depends, as you saw in the beginning. Smoke can be can be transparent. This is why, for example, thermal hotspots can be detected below smoke, but not below clouds. It's more difficult. Be careful with resolution. Resolution means, if you have a coarse resolution, means that you don't know exactly where in that pixel it burned or it's burning. You know that in that pixel, part of it or all of it is burned or it's burning. So be careful with that. What else? In terms of main limitations, I think that's it. And then, of course, again, pay special attention to the start and end of the progression to avoid major fire behavior underestimation. So I think that's it. I would just like to add this final kind of advertising slide, which is, if you want to know more on wildfire reconstruction, wildfire spread reconstruction, we have 2 more workshops planned, which will be still to be confirmed in Germany in November, not online, at least to the best of my knowledge, and then for sure not online in Lisbon, in what we want to call it the kind of winter school on fire spread reconstruction, where we will, let's say, move to an advanced level and trying to use not only the satellite data, but more satellite data that we did not talk about here today. For example, the geostationary data. We did not talk about this, and it's useful, although it's coarse. You will see that it's very, very useful. And then more advanced in the sense that we are going to merge with thermal data from airborne, field data, etc., and put all of the pieces together and build the puzzle, reconstruct the puzzle. So these are the 2 workshops that we have scheduled. And then I would like to highlight again the importance and the opportunity that we have with the short-term scientific missions, and would like to invite anyone that is interested in wildfire reconstruction to visit us at the University of Lisbon. We are more than willing and happy to have you here, working on reconstructing fires from your country or working on reconstructing fires from Portugal. We have a lot of data to use, so that's that could be also interesting. If you're interested in doing that, contact me for more information and visit the NERO Network grants webpage to know how to apply for a grant. It's super easy. It's just a question of wanting to take that opportunity to learn a little bit more. So that's it. Questions?
I have 2 questions in the chat. Yeah, Johanna, I think.
Raised.
Yeah, yes, Johanna is, I think, the first one to. Okay, so please, Johanna.
Hi, good morning. Can you hear me?
Yeah, great. Thank you.
Okay.
Yes,
First
we
of
can
all,
hear
thank
you.
you so much for this. Thank you so much for this webinar. Super interesting. I had a question regarding like the effort or manual effort, I suppose, that it took to make this data set, because actually I know that there is a whole data set for fires in Portugal. And I was just wondering how much like effort you would guess constructing this data set was, like how many hours did it take you, and maybe if you see a way of automating this, or do you think it will only be possible with manual effort?
Thank you, Joanna. Very interesting question. The short answer is it took too much time, too many days. So adding new wildfires, it was all manual. So adding new wildfires cannot be done manually anymore. It's too much. I mean, you can do it for one fire. I mean, this one took, I don't know, I think net time, at least 1 week of work, easily, because it's not only the satellite data, and it's not the satellite data that takes most of the time. It's the airborne data, and it's the field data. That is extremely, extremely difficult and laborious. It takes a lot of time consuming. Yeah, it took too much time. I would say that an average fire takes around 1 day to reconstruct using, if it's not too big and if the images are okay. We're actually moving towards, so the civil protection, which operates 2 airplanes with thermal imaging, is moving towards and is now has a system implemented which is much better than the previous one, which basically takes thermal maps of the fires. That's super useful, because even if you do it by hand, and actually you don't need it to do it by hand, but you don't need to interpret the images one by one or videos one by one. That's very useful. So your first question, yes, took too much time. I would say more than 1 day, around 1 day for a 500, 1,000 hectare fire with good images, Way forward, we definitely need to automate methods. That's a must. Otherwise, this will be it won't be sustainable to continue and to build a database like this. I think for the remote sensing part, it shouldn't be difficult to automate methods. It's an area which I haven't invested any time, to be honest. Although people from my lab have implemented some automatic methods, we just never got the opportunity to do it together, but we will, I think, in the future. So there are some image segmentation methods that probably would be useful. The problem is the airborne data. There are some methods to look at the airborne data, either videos or photos, and georeference it, and then segment it and classify it in burn, not burn, active, not active. But not only, I think the methods are not, let's say, the easiest ones to use and the ones that providing the best results possible. Most importantly, not all of the data recorded by the local entities has enough information to apply these methods. So meaning that if they do not have, and I'm moving a little bit outside of my area, but if they do not have the relevant metadata in a video taken by an airplane, if you don't have the relevant metadata, you cannot basically place on the ground, on the surface, what you're seeing on the screen. And if you cannot do that, you cannot map it. I would say that's the biggest limitation, and I encourage anyone that is interested in working on that to move forward and to reach us, because we're super interested in doing that. And also the satellite methods, the automated satellite methods, we definitely need to improve on that. Yeah, it's a very important topic. Thanks for your question.
Thank you so much.
Liliana?
Yeah, on my screen, Gabriel is next one with raised hands. I propose that we deal with the hands first, and then the questions from the chat. Okay.
A very quick question. Please repeat where we can find first of all, congratulations, very nice presentation, step by step. The second one is, where did you say we can find information that we have prepared regarding how to download images and first steps?
Yeah. Thanks, Gabriel. Let's say the protocols for the detailed protocols for downloading the imagery, it's on the end, at the end of the presentation, where I have some annexes. Okay. So atmospheric correction, pixel size deformation, satellite time span, and then here it is, working with data from Sentinel EO browser. So I added two, working with data from Sentinel EO browser, and creating your own composites. It should be super easy. I just noticed it that I did not add information how to download it, but I can add it here. There's basically a button here that has been cut for space reasons where you can download. But I can add that information also here. And then the other one is downloading and processing VIIRS hotspots from VIIRS. This is a step-by-step guide, let's say, with 8 steps. And yeah, what else? I mean, we could also provide you. Let me just check one thing. Sentinel-2, Sentinel-3. Okay, yeah. We could also provide some information on MODIS and VIIRS. So just the images, but it's those ones are really easy. It's basically taking a snapshot and downloading. These are the most, let's say, complicated ones, which are not complicated at all, but take a little bit more time, and the details are here. That covers it, right, Gabriel? Okay. Send me an email if you have any doubts on any specific data source or product. Yeah, go ahead.
Yeah, thank you, Gabriel and Akli. And Domingos, if you raised your hands, if you would please state your question.
Thank you very much. Hello, Akli. Many congratulations for your presentation and for the nice guidelines that you are giving us. This is very useful to analyze these very large fires. And I would like to stress the point that you made about the need to have accurate time and distance measurements, because the rate of spread can vary, let's say, quite a range, as you showed. And we are actually studying these quick changes on the rate of spread, and especially for the complicated fires like this that create problems of safety. We are looking at the changes in the rate of spread in shorter periods even. And as you may know, my team also studied this fire, and we did lots of field work as well. And we got, let's say, other information about some details on the propagation that can be caught by other means, but I think that the satellites don't get entirely. I'd like to have your comment about this, because sometimes you are looking at very quick phenomena that are not caught by satellites at the present time resolution that they have.
Yeah.
Okay.
I totally agree. That's a very relevant point. The time window. So there are several limitations, like I mentioned previously. But let's say that the main one is you're basically taking a picture, and then you're traveling around the globe, and 12 hours later you're coming back to the same place, if you're lucky, because some satellites just come back almost 10 days later. So you lose a lot of information. Part of this limitation can be, let's say, attenuated by using several satellites. And I think the question from Dan was very interesting in that sense, which is if you can start using constellation, I think, well, for sure the way forward is to use constellation of satellites, increasing the time frequency with a reasonable spatial resolution. But still, we're going to lose a lot of the information, and this the specific aspect that you were mentioning, which is rate of spread, has short to medium-term variations that are very important and very relevant to study. And those are more difficult to capture with satellite data. They can be captured in the sense, well, you can attenuate the effect, as I said, by combining several aspects. But again, the best, let's say the best interval you will have will be around, well, the best, no, let's say the average interval that you will have will be around 8 to 10 hours, which is something in an observation at 2-3 p.m. If you're lucky, let's say 2-3 p.m. and then something around well, I said 8 hours. No, it's more, 12 hours, around 2 a.m., 1 a.m. So that's a limitation. Of course, sometimes you have smaller intervals, like something at 10 a.m., 11 a.m., and then at 3 p.m. So 4 or 5 hours of difference. So yes, that's a limitation, but it's extremely useful. First, to have an overall idea of the global patterns of fire spread. That's extremely useful. Not to have the fine details, but the global patterns. And second, it's extremely useful when you're using this to merge information at the finer scale. Field data, interviews, as your team also has done a lot of work on that. Airborne data, so videos taken from an helicopter, videos taken from photos. Marcos will show some interesting things in the next minutes regarding that. The videos or photos taken by airplanes, etc. Those are when you put all of those pieces together, satellite data, the value of satellite data increases. And yes, there you can have, let's say you can start capturing those smaller details. The best way to capture the details would be to have an airplane flying 24/7 on top of a fire. That would be, so no clouds would get in the middle. Well, smoke would be a problem, but no clouds would get in the middle, and you would have frequent and permanent observations. Unfortunately, that's up to date, not possible, not feasible. Yeah.
Thank you very much.
Thank you. Liliana, should we move on to the chat?
Yeah.
We still need to leave some time to Marcos, otherwise it's going to kill me.
Yes, yes,
Maybe.
there are few questions in the chat. If you could maybe shortly address them.
Yes.
Yes, Johanna asked, how do you calculate the rate of spread? Because it differs depending if you take it as a starting to end point in different direction.
So I will address Joanna's question and also John's question.
Yes, and so, how does the final rate of spread?
Yeah. So the rate of spread is basically the speed at which fire travels, let's say, or spreads from one point to the other. That's rate of spread. Okay. If you're talking about the head rate of spread, which is what most people use in modeling or even in fire behavior analysis, it's the head rate of spread, meaning it's the fastest moving part of the fire. And that's usually that's in the head by definition. So going to Joanna's question. Yeah, going to Joanna's question. Yes, you do need to say this is the start point and this is the end point. How do you calculate that? Maybe I can provide you more details in by email or something like that. But in concept, it would be something like, this is my first progression, and then this is my next progression. Let me see what was the area, the place that you had a larger distance covered. So that will be the head of the fire by definition. It's the area that spread the most. Once you know where it ended, because you draw the polygon of progression, and once you know when it started, because you have the polygon from the previous progression, you have the start and the end point. You have the time between both polygons, you can calculate the rate of spread. So And I'll address also John's question. The rate of spread would be best calculated in the direction of travel. It's not the direction of travel. It's in the direction of the highest distance traveled, which is the head of the fire, not the wind direction. I'm sorry, but that's not correct. It's not the wind direction. It's the direction where the fire spread the most. That can be coincident with the wind direction, or it can be not coincident with the wind direction. And we can discuss this for hours. But if it's a topographic fire where wind is not a factor or a relevant factor, probably the head of the fire will be aligned with the slope direction and not with the wind direction. So to avoid doing that, the definition is the rate of spread, the head rate of spread is the speed at which the head travels, meaning the part of the fire that covered more distance in the same period of fire. Okay, you can calculate flank and backing spread rates. For some people, it's relevant, and it depends on what you're studying. But that's the flank rate of spread. It's not the head rate of spread. Okay. Once you have I think the most important thing is to say, once you have two progressions, consecutive progressions, you know the start and the end, you can calculate the rate of spread in any part of the polygon. Let me go to the next question. The head of the fire equals to forward rate of spread. Yes, exactly. In your opinion, would it be a good idea to use other layers of information, such as burn severity or intensity of the fire, the NBR or an index, and the type and structure of vegetation considered as proxies to a better understanding of fire behavior in those grounds we have obtained from satellite imagery? Yes, I mean, first, intensity and severity, of course, are different concepts, which are usually confused by many. Not saying that's the case with you, but these concepts are commonly confounded, let's say. You can use whatever you want to try to understand why a fire behaved like that. The idea of using the satellite data to reproduce the fire spread is to say the fire spread like that. So this is what I observed. This is what I observed in terms of progression and spatial and temporal pattern of the fire. Once you do that, you can calculate behavior, the forward rate of spread, fire line intensity, growth rate, etc. Once you do that, you can go and try to understand why. So either why did this happen in terms of vegetation structure, weather, etc., or you can go on the other side of, let's say, on the other side of the coin and say, what impacts did this fire behavior have? And for that specific question, DNBR, severity estimates, etc., are very useful, of course. So I would say that what we were talking about in terms of satellite imagery is observation of what happened. Then we can go before and say why this happened, and can go after and say what were the consequences of this happening. Okay. No. Okay.
There is one more question regarding MTGs.
I just don't know the name.
Yeah.
So, yeah, you said MTG satellite will be still very coarse, but for large fires, don't you think they could be used for monitoring the more active areas and at real time with very high resolutions? Contaminated pixels can be very limiting, I suppose. I'm excited. I'm waiting for the launch of well, not the launch, but the availability of that data. We have used, we were lucky to use GOES data to reproduce fires in Chile with some colleagues and friends from CONAF, and just moving to between 1 and 2 kilometers. So for 4 to 1, around 1 kilometer around 2 kilometers in Chile, the difference is huge. And the benefit is it's much bigger than just saying the resolution is half of the original, because in fact 1 pixel is divided in 4 when you do that. So the amount of detail it's much higher. So I just think that if you have a small fire, 100 hectare fire, drawing progressions using MTG data is probably not going to be feasible. That's it. But as you will understand, if you attend the next workshops, there is a lot of added value by using these geostationary data, even the MSG, because they provide fire radiative power measurements, observations, estimations every 15 minutes. In this case, we will have every 10 minutes the amount of energy being radiated to the space. So that is extremely interesting. And for example, what Professor Viegas was saying, this can connect very well with that, which is we know, and we have seen that in several fires in Portugal. We have a lot of oscillations between the start and the end of a fire in terms of energy, which are, let's say, translated in terms of energy released. MSG does a very good job, especially for big fires, in capturing that variability. So it goes up and down, and then it sleeps for a little, and then maybe goes up again, wakes up again. MTG will probably be much better. So I am from the side of the excitement, not the side of, oh, it's not going to work and it's not going to be useful. It is going to be useful. What else?
I think these are all questions. The others are just compliments on your presentation.
Thank you for that.
Yeah.
How does the last final fire spread database look like? Just a quick answer. It's a bunch of polygons with progressions and then with fire behavior descriptors calculated for each progression. If you're interested in looking at Google the PT fire spread database, and you will get an idea of how this work is multiplied by 80 fires, more or less how it looks like. So Jürgen Robot, if you combine the isochrones with a topographic map, it's feasible to calculate the rows on slopes, or is it not useful to do that? The isochrones need to be combined with a topographic map, meaning that you need to calculate, if you want to calculate the rate of spread in any direction, especially the forward rate of spread, you need to know the topography, because only with the topography you can calculate the actual terrain distance. So the actual distance covered by a fire on the ground. And that's the actual distance he traveled, not Euclidean distance, okay? I think we do need to move on, otherwise Marcus will be upset. Presentation will be available. Video will be available. So now we'll move to a different topic. It's a shorter presentation, and I think it's super interesting, so don't leave. It's the NERO fire collection application that we have developed, and it's to be used by NERO members. Marcus, if you can start sharing, I can introduce you. I'll stop sharing. Did I stop sharing? Oh, okay. Okay. So just introducing Marcus very briefly. Marcus is a practitioner, fire operative. He's a firefighter from Força de Emergência e Proteção Civil from Portugal, and has been doing super work with us, considering regarding a field data collection application and dashboard, where that can be used for any NERO member to collect data on the field. It will be extremely useful to reconstruct fire spread. Go ahead, Mark. The floor is yours.
Thank you, Akli. Hello, everybody. Nice to see some familiar faces and names around the close to 70 participants in the workshop. First of all, I would like to say thank you to all of you that send your doubts and your contributions via email. I've tried to add them all to this presentation, so I hope I can clarify some of your doubts today. Moving on. So, like Akli said, this is a very brief presentation. We're going to talk about where you can download the applications, A brief explanation on how everything works. So in this part, I believe many of our doubts would be clarified. Then again, we'll see in more detail the field maps app and the quick capture app, and then you can see also a preview on the dashboard where all the data is combined and can be viewed. Okay. So you can download in the correct names. This was a doubt sent to me by a colleague of NERO. The correct names for the applications are Esri Field Maps and Esri Quick Capture, and they can be downloaded from Google Play, or if you have an iPhone, you can download it via App Store. It's important to clarify right now that these are redundant apps. This means that they operate on the same layers, on the same published layers, so it doesn't really make a difference whether you choose one or the other to collect the data on the field. They both have pros and cons, and we are going to talk about that in a short period of time. So how everything works. These apps are based on GIS applications, so they work on layers. Those layers are published in the cloud service on the Esri software. So once they are published there, we can all add from everywhere as long as we have an internet connection. We can add information via smartphone, with a tablet, if you like, a laptop. So as long as you can get access to the information, you can add all kind of information on the fly. So with that being said, you can help reconstructing the wildfire spread using data on the field, and this will enrich the analysis much more and will complement every phase of the process. You can do a fire progression with a time tag on, so you know exactly when and where that fire progression took place. You can do videos, you can do photos. So yeah, this application will surely be of much help to everyone. So starting with the applications, the Field Maps app to me is the most complete one. It combines 3 old Esri maps. I don't know if you are familiar with this software, but it's very powerful. It's a combined version of 3 different apps, like I said before: the View app, the Collector app, and the Track app, all merged into this one. So it's map reading app, so we can view all the time when you are creating, when you are inputting something, you can know exactly where you're putting it. So it goes exactly where you wish to go. Unlike Quick Capture, you cannot visualize where you're adding information. Field Maps, you can do it. So it combines map reading with data collection. It offers the possibility to, and this was also a doubt shared by many other NERO users of these apps. It's whether or not this app could be used offline. It can be used offline. I will explain how in a moment. You can share information. The only limitations to me of this app is that it doesn't allow data analysis on the fly or data filtering. But for everything else, it's a very complete field app. Okay, so once you download the app, you go to sign in with ArcGIS online credentials, and this you can see you have another option to sign in with ArcGIS Enterprise. Regarding some doubts that was sent to me, Joanna is sending a message. Yeah, I can share the link later on. And then with ArcGIS Enterprise, this app could be much more than it is today. You can do automatic calculations. We can put automatic country on the field, so we don't have to fill it by hand, and many other things. With ArcGIS Enterprise, it would be like this app on steroids. So after you sign in with ArcGIS Online, you use your credentials. If you do not have a credential, you can ask Akli via email your credentials, and Akli will surely send it to you as soon as he can. And then on field maps, you have two possibilities. You have the NERO map. It's the one you will use when you have internet signal, and the NERO offline map that you will use when you don't have, or you don't expect to have telephone signal. What you have to do is you cannot go to a wildfire and say, well, I don't have the internet signal, so I now will have to use the offline map. No, you will see later on that you have to previously download the area before you go to the field. Okay. Moving on. Once you get into the app, this is, again, it's a very simple app. We can do a lot more than we did so far. So we ask again for your contributions of anything you wish to see added here, and I will gladly do it. So if you see on the bottom right side of the screen, you have a little plus sign. If you select it, you can choose which feature you would like to add to the map, and just select it, and you will open a pane with several fields for you to fill in, and then just submit. I highlighted the pictures videos because it has a field. It has an interesting field here on the right side that says direction, and I put it degrees here so you can more easily see what you need to put here. Let's say, as you can see, the symbol on the pictures and videos has a little arrow. So if you do not put anything here in the direction and submit the point, the arrow will always point north. Okay, and so let's say if you are facing east when you took the picture, you choose 90 degrees, and the symbol will automatically turn to the east. Again, we are using ArcGIS Online. If we were using ArcGIS Enterprise, that I could automate this, and this field will have no need. The other points are exactly the same. You do exactly the same thing. It has the same fields, apart from the direction in degrees. There are no direction in the other points or in the fire progression. But let's say you are like me and you wish to fill in all the fields, and this would be very, very time consuming to do it for every point you need to add to a map or a scene. So one thing you can do to make things faster is to, let's say I want to add another point with the exactly same number. Let's say the same fire ID, because I'm in the same wildfire, and the same country. So I select the point, as you can see in the image on the left. You scroll down until you see copy attributes, and then you choose the new point you wish to add, choose the location, and done. You copied all the attributes from one point to another. This makes the data collection much faster. One other cool feature that field maps have is the GPS link. So let's say I'm not in a wildfire, but I wish to go to a wildfire. So I select a point or a polygon. I scroll down until I see directions, and then I choose my preferred GPS application, and then it will be just like going in a car to visit a city or something. It tells you exactly where you need to go to go to the wildfire. On the top right hand side of the application, you have 3 little dots. If you click there, you will see several possibilities. Please explore it a little bit. I will address only few. You have a base map that you can choose. You can choose this little gray map like I am showing you right here, or you can choose real image like this one. You can choose either one that suits you best for your data visualization. Let's say, for instance, I would like to see the hotspots from MODIs and VIRs. Maybe this gray map is better for this visualization, so you can choose it and change it whatever you like. You have also bookmarks. Let's say if I have 3 or 4 wildfires in the same country, I can zoom in on one, click on bookmarks, add the name, go to the next one, add another name, and then I can easily change between wildfires without having to constantly zoom in and out of the map. You have the legend, you have markups. This markup tool, it's for instance, look, we have to prioritize the right flank, and you do a little markup, and you can share it with the other members of your team, so they can see exactly what you mean. And then you have the search tool up there as well. You can search. This was also a doubt that came to me by email. You can search coordinates. I've tested only lat long coordinates, but you can search it. Let's say someone sent you a coordinate point of something like maybe an hotspot or an active fire. You can search it directly here on this symbol on the middle, and automatically go there. That being said, if you wish to use offline map, you have to choose it on the beginning. You go right here on the access maps, you go back, and then you choose NERO offline. Again, this has to be done before you go to the wildfire. You have to download the area previously, okay, and then work on that area. It's like doing a mini map of an area you would like to explore. So you can click those three little dots. You can choose add offline area, and then this image right here on the middle will appear. You zoom in as much as you can to the wildfire when you are sure or almost sure that the wildfire would not leave this frame, and then you click download area. As you can see in the image on the right, the area would be downloading. Once it is downloaded, you can go, and then you can use it offline and sync it with the online version whenever you have internet signal. Moving on to quick capture. Quick capture. What the pros to use quick capture are the faster data collection. It can be used offline with a little trick, meaning it doesn't really work offline. But if you do have internet signal, once you open the app, you can continually to take points and to gather information, even if you don't have internet connection. And then when the app goes to an area where it has signal again, it will automatically sync it to the online version. So again, it can be done. It can be used offline with that little cheat. Again, it doesn't need a map, but it's also a con in my opinion. You don't really see where you are putting your points. It has to have a limitation of 330 meters. Okay, so if you do not have GPS satellite better than 30 meters, it will not allow to take you the point. But down here you see GPS accuracy. It will turn this little circle here will turn red, and you don't have the possibility to take any points. So in the top right corner, this symbol right here, if you do see little numbers here like 1, 2, 3, 4, or 5 are the information or the points that are to be synced. They weren't synced at the moment. So anyone that has the map opened on another platform, whether it's on laptop or on tablet or on the other phone on field maps, will not see the information until all the items are synced. The first button is a direct link to NERO project, and why under that is the take picture video button. It's very much simple to use and to explain. You just click it, and your camera will open. You choose if you want to take a picture or a video, and once you are finished, click again, and that's it. You will appear on the top right side when it's done. The other points are very much similar. You choose the point and just click it, and once you click it, it's done. It's very fast. to draw the polygon. This was also a doubt of another NERO use it. To draw a polygon on this app, I don't advise it because it's very time consuming. If it is a big wildfire, you cannot do it because you have to click draw polygon. It starts doing a polygon by its own, but you have to go around the entire fire perimeter and click it again to stop in order for it to do a polygon. It's much easier to do in field maps because you are at a higher point watching a wildfire and you can draw it. You can draw it simply by just looking at the app and looking at the terrain. This is the visualization dashboard. Again, it can be done. Another colleague of NERO asked if I can do another tab right under here with the pictures that is taken. I can do it. Can also be done much more with this. So yeah, please send me your questions and your contributes to, so we can continuously improve the app. Okay. So at the top corner we have the select date button. It's pretty much straightforward. Just select the day that you want, and you can see all the information is filtered, and you see only the information on that day. Here in the number 2, we have these three lines. Just has a link to the project NERO and to end the session. The search bar, again, very much similar to the field maps. You can search by location. You can search by, let's say, a point. If you choose a point and you give it a name, you can search it on this search bar. If you do zoom ins and outs and you wish to come back to this view, you can just click on the little house button at number 4. Number 5, you have the legend. Number 6, you have all the available layers. Right now, we only have the layers that we created for this project and the hotspot. But like I said before, we can add much more. All that you see necessary. Number 7 is the base map, so you can change the base map. Number 8 is a compass. So if you right click on the map on the dashboard, you can turn the map around to any orientation that you like. If you wish to come back to original orientation, you just click this button, and the map will automatically be headed north. The button number 9, if you are using a mobile device to access the dashboard, it will zoom in on your location. The number 10 will do zoom in and out. And if you press the tab on number 11, you will see this dashboard with some statistics. Right now, the only statistics available are the number of records by user, but we can do much more with it. We can say how many wildfires are per country and much more. And that's it. Very brief. I don't know if anyone has any questions. Please go ahead.
Thank you, Marcos. Very clear.
Thank you.
Any questions? Apparently not.
Either everything is clear, or nothing is clear.
Okay,
Yes,
Joanna.
we have one question.
Please. Oh.
Can you guys hear me again?
Yep.
Okay, perfect. Thank you, Marcus, as well. Really interesting. I was just wondering about how to access this information and whether there's also maybe some way to download this, or is it only possible to view it in this viewing app, either on ArcGIS or in the dashboard?
Yeah, you can download it if you have an account. If you have an ArcGIS account, you can add those layers to ArcGIS Pro, and then you can export it to, let's say, KML or KMZ or shapefile, anything you like, you can do it. The dashboard only allows the statistics. You can download it to a CSV file. If anyone has any interest, you can do it directly from the dashboard. Regarding the layers, you have to have an ArcGIS account to visualize it and download it on the software.
Right, perfect. Thank you so much.
Let me just clarify one thing that I think it's important. Of course, the app is and the dashboard are free to use. We want you to use as much as possible. I want to make this very, very clear, and urge you to use it during this fire season, during next fire season, whenever. You do need to be an NERO member, which is, I mean, you don't have to pay anything, so you just subscribe to the NERO network and that's it. And once you do that, please send me a request for a user and a password. That's as simple as this. You register, then send a request, and I will give you a user and a password, and you can use it to add data. Remember, all the data that you add is visible to all people. So, and it's important that, and I want to stress this, it's important that you try to provide as accurate as possible the data, because that will be one of the sources of data that we will use to reconstruct fires during NERO, or you will use maybe to reconstruct fires in NERO during NERO. So that's important. All of the data that Marcus showed is just records that we were playing around with the application. All of those will going to be deleted, and we're going to start from fresh in the next few days. Okay. So these are the steps. Any other questions?
The presentations and the recording will be available?
Yes, both. Yes. I will have to do probably some editing of the video. I'm not sure. That may take some time, but not much. And the presentations will also share through the webpage and maybe through social media also, just for you to know that it's there and it's available. But yeah, in the next week we'll put everything available if possible. And send us comments if you remember of anything, comments or questions or whatever. Feel free. And if you're interested also in taking the opportunity of using the short-term scientific missions, go ahead. We encourage you to do that, and we really like you to do that. So you in general, of course, the plural. Yeah. Any other questions for Marcus or any burning topic? If not, I don't see any hands. No. Oops. Oh, this is a clapping, not a hand raise. Okay, thank you, Jürgen. If not, then thank you very much. It was a pleasure to be here in the first of many, I hope, NERO Network cafes or webinars, workshop, or whatever. Hope to see you in the next time, and take care. Have a nice weekend. Bye bye. Thank you.